Okay, so yeah, like I said, these are connected to the notes we did from the last set of notes from solving, separating by solving. The reason I did that is because it does the same thing. Slope fields do the exact same thing that these notes did when we did them. It's the exact same process. You can solve using slope fields. Why do we use slope fields? Because it's just a graph, it's pictures. Okay, it's a visual representation of what you guys have been doing. Okay? So a slope field, sometimes it's called a direction field, is a graphical general solution. So it's a general solution and can also be a particular solution. So to create a slope field for the first order differential equation, dy dx, we would set a plot. We're going to make little segments at each point. Okay, so it's a lot easier than it looks. So we're going to make a slope field. The differential equation for this one is dy dx equals 2y. So how do we do that? Well, each of those dots is a point, right? 0, 0, 1, 0, 1, 1, 1, 2, right? Okay, so instead of the axes, they put dots. Okay? So for what we're going to do is we're going to plug in each point into the differential equation. When I plug in something to the derivative, what does that give me? Review from last semester. Slope. It gives me a slope at a specific point, right? That's why it's called the slope field. Okay? So slope fields will tell me the slope at a specific point. So for example, let's start with the first point. Let's start with the first point here. 0, 0. Okay? So at 0, 0, this point is, you don't have to write this part down because I'm going to erase this in a second. I'm just showing. So at 0, 0, I'm going to plug it into my derivative. Okay? So in other words, dy over dx equals 2y, right? Well, at 0, 0, I should actually write it like this. 0, 0 means I'm plugging in 0, 0 to the derivative. I don't have an x to plug in, right? But I do have a y. What's the y? 0. So what's the slope of the tangent line at 0, 0? 0. Okay? So I'm going to go over here now to that spot. What does a 0 slope look like? If you could do it with your arms, like what does a 0 slope look like? Completely horizontal, right? All run, no rise. Doesn't rise at all. We're going to draw a little picture just like that. So here we're going to draw a little segment with a 0 slope. Okay? We're going to move one over to the right. You can go anywhere. You can start anywhere. I just have to fill in all of these dots. Okay? So let's go to the right. The right is 1, 0. So for 1, 0, I'm going to plug it in. So the derivative is dy dx equals 2y. So what do I plug in? What's the only thing I can plug in? At 1, 0. Remember, I'm at 1, 0 now. Still 0, right? I can't plug in x because there's nowhere to plug in an x. Still 0. So the derivative at 1, 0 is what? 0 again, right? There's a little bit of a pattern here. I got 0 twice. Where else am I going to get 0? Do you know anywhere else I'm going to get 0? What other points I'm going to get 0 at? 2, 0. That's one of them. What's the other points?
Anything on the x-axis.
Anything on the x-axis. Because y is 0, right? On the x-axis, y is 0. So I don't even have to do the math. I know that anywhere on the x-axis, y is 0. If y is 0, my derivative is going to be 0. Y equals 0. Anywhere on this line here, y equals 0. Right? Okay. Let's go up a row. I'm going to go up. 0, 1. 0, 1. dy over dx, 0, comma 1. So plug it into my derivative equation. What do I plug in for y here? 1. So I get a slope of 2. So again, this is how I kind of do it in my head. What does the slope of 2 mean? Up 2 over 1, right? Up 2 over 1. So I kind of look to see with my arm, like, what does that look like, right? So up 2 over 1, if I was going to go up 2 over 1, that means I'm going up 2 units and over 1 unit, right? To connect, I would look something like that, right? So I'm going to try to draw a little segment that looks like that. Now, is there anywhere else I'm going to have a slope of 2? Anywhere else I'm going to have a slope of 2? Anywhere, any of those other dots?
The whole line.
Everywhere y equals 1, right? Everywhere y equals 1. Okay. Everywhere y equals 1, I'm going to have a slope of 2. Let's go up to the next row, where y equals 2. What's the slope there going to be? 4, right? Because 2 times 2 is 4. So what does the slope of 4 look like? Well, slopes of 4 is 1, 2, 3, 4 over 1. So this one's going to be a little more vertical. A little more vertical. You just try to draw the best you can. Everywhere y is 2, it's going to have a slope of 4. So when you look at this, I don't know, if I didn't do any of this, I don't know what these slopes are exactly, but I know they're positive and I can compare, right? I can compare and I can say, okay, these all look the same. These all look the same. And I can say these are a bigger slope than these, right? That's all you need to say, because sometimes they'll just give you a picture like that and you just use, so you don't have to be specific. Like if I just looked at this the first time, how would I know that these are positive 4 slopes? I wouldn't. I would know that they're positive, right? They could be positive 3, positive 5, somewhere around there. You could estimate them, right? That's why slope fields aren't the best way to do. They're just for approximating. They're visual. The reason we do them is because they're visual. And anything that's visual is easier. Okay? So let's go down 1. Y is negative 1 here, right? What's the slope going to be? Negative 2, right? Negative 2. So again, negative 2 down 2 over 1. So it's going to look kind of like that. Kind of like that, right? And then the last row, what's the slope going to be? Negative 4, right? So more steep going down. There's your slope field. That's a direction field, slope field. It's called a direction field because slope is the way you're going, right? You're either increasing or decreasing or staying the same. So that's why it's called a slope field or direction field. Okay, that was part A. Fill it out. Part B says, suppose that you know that 0, negative 1 is on the particular solution of a differential equation above. So this guy here. By following the slopes, draw on the diagram above what do you think the particular solution will look like? Okay, so when they give you a dot, start there. So I'm going to go make a dot at 0, negative 1. That's right. 0, negative 1 is right there. right? So what they want me to do is draw what the particular solution is going to look like. So how do I do that? You use the directions. You use the direction field, right? The slope field is a bunch of directions, and you just kind of go with the flow. So if I'm going to go to the right, so from here, if I'm going to go to the right, am I going to increase or decrease from there? Am I going to go up, down, or stay the same? Decrease, because the slope is negative, right? I'm going to go down this way, right? So I'm going to kind of draw that. I'm going down that way. What about as I go the other way? Yeah, I'm kind of going up, right? I'm kind of going up, except I can't cross. Why am I not going to cross the x-axis? Because the slope is 0, right? And if a slope is 0, that means it kind of, so as I get closer to the x-axis, I got to kind of straighten out. Okay? So that is the particular solution at 0, -1. So it's what you guys did last time when you separated them and then you plugged in a point and then solved for y. That's what we just did there, but as a picture, as a graph, instead of doing all that, okay? Note, the graph will follow the pattern of the slope field, but may go between points besides those. So it kind of, goes between, might go between. That's what it says, okay? Okay, so now part C wants us to do it the old school way, the way we did it the last couple days. They want us to separate and solve that way, okay? And compare our results. Okay, so here we go. We have dy over dx equals 2y. What was the first step for the way we've been doing it? Yep, x is on the right, y is on the left. X is on the right, y is on the left, right? So I got to multiply both sides by dx. And then I'm going to divide by 2y, right? So I get 1 over 2y dy equals 1 dx. That was the first step. What did we do after that? Integrate, right? Antiderivative. So for this guy, what I would do for this guy is move 1/2 to the front. So I get 1/2 and then 1 over y dy. Okay. Move this over here. Okay, so what's the antiderivative of 1 over y? Natural log of y. Yep, natural log of y. And what's the antiderivative for just 1?
X.
Just x, yeah. Just x. 1x to the first power divided by 1. Okay? That was step 2. Step 3, plug in your points. Plug in your points. So I plug in -1 for y and 0 for x. Oh, oops, I forgot about a plus c. Plus c, I forgot about that. Okay, so when I plug in a -1, remember, I can't have a negative natural log, so that's when I need the bars. I can't have a negative log. So it's going to be, it really is the natural log of 1. So c equals 1 times, what is the natural log of 1? 0. So it's really 1/2 times 0. So c equals 0. Okay. So let me go over here. 1/2 natural log of y equals just x, because c is 0. Last step, solve for y. So remember how we did this, I think yesterday, definitely yesterday. Remember, if I want to change a log, so really it's this, right? And I use the loop trick. Before you do this, I should probably multiply both sides by 2. Get rid of the fraction in front. Multiply both sides by 2. And then do the loop trick. So I get e to the 2x equals y. Just changing it from log to an exponent. Okay? So part A and B is what we're doing today. Part C is what we've been doing the last few days. That's the difference. They're both exactly the same. Okay. Alrighty. Okay, so now what I want you to do is do part A. I want you to sketch, give me the slope field for that differential equation. Now you have an x, so I can plug in x and y. So let's do the first one together. I'll do the first one with you. So dy over dx for 0, 0. So what's the slope at 0, 0? Well, I'm going to plug in 0 for x and 0 for y. So when I plug in 0 for x, I get 0 minus 1 over 0 squared. Negative 1 over 0. What does that equal? Starts with a u. Undefined. Undefined slope. What does an undefined slope look like? Slopes can be undefined. What do they look like? If a 0 slope looks horizontal, it'd be vertical, right? Yeah, it'd be vertical. It's going to be vertical. Just like that. Where else? Why? So my question is, why was that? What caused that to be undefined slope? Because y was 0. So anywhere y is 0, it's going to have an undefined slope, right? So where else is y equals 0?
All across the x-axis.
All across the x-axis. So anywhere across the x-axis, you're going to have you always look, because I have to fill out, there's 12 dots to fill out. On the previous one, there was 25 dots to fill out, right? I don't want to have to plug in all those things. So you look for patterns. Look for patterns so you don't have to do that.
Are they always the same across, like, what is the word? Each row?
I think I know
Are
what
they
you mean.
Always the same?
No.
No.
Sometimes they'll be different, yeah. We'll look at some. On the next page, I have a whole bunch of them.
Okay.
And there's definitely always going to be patterns, though.
Okay.
There's always going to be patterns that you can tell. Always look for those patterns to save yourself time. Yeah, that's always a good idea. Okay? So what I want you to do is tell me what the other 8 dots are doing. Tell me what the other 8 dots. And again, just do the best you can. Mainly, is it positive, is it negative, increasing, decreasing, 0, undefined. So anywhere x is 1 besides 0 is going to have, you're going to have, because if I plug in 1 for x, that's going to be 0. 1 minus 0. The only place it won't be 0 is at 1, 0, because y is also 0. 0 on top of a fraction, you get 0 unless there's a 0 on the bottom. At 2, 1, at 2, 1, it's going to be positive 2. At 2, 2, it's going to be positive, but it's going to be actually positive 1/4. So very almost flat. At 0, 1, it's going to be negative. At 0, 1, it's going to be negative 1. 0, 2, it's going to be negative, but it's going to be negative 1/4. At negative 1, 1, you're going to have negative, what is that, negative 2. And at negative 1, 2, you're going to have negative 1/4. A lot of that you can do in your head. If you can do that in your head, I'm fine with that. Because you're just plugging them in. Okay? Okay, part B says do it the way we've been doing it. Solve and see what we get. Okay. So, start with dy over dx. dy over dx equals x minus 1 over y squared. What's the first step? Multiply by dx. That'll get y's on one. That'll get dx on one side. How do I get rid of the y on the right side?
Multiply by y squared.
Multiply by y squared. Yeah. Why am I doing that? Okay. There we go. Multiply by y squared. Okay. So I'm going to get y squared dy equals x minus 1 dx. Integrate. I'm going to get 1/3 y cubed equals 1/2 x squared minus x plus c. Plug in your point. So we get 1/3 and 1/2 minus 1 plus c. So 0 is x, y is negative 1. So I'm going to get negative 1/3 equals 0 minus 0 plus c. Okay. So I get 1/3 y cubed equals 1/2 x squared minus x minus 1/3. Solve for y. Multiply both sides by 3 over 1, or just 3. You can distribute or not distribute. It's up to you. Take the cube root. Cube root. So y equals the cube root of 3 times 1/2 x squared minus x minus 1/3. There you go. Okay. So it's kind of half what we've done, half new, the slope fields. Okay. So the last page, the very, very last page of the notes, the very short notes, because really it's slope fields, that's the only new thing, right? Is just, I gave you a bunch of slope fields to kind of play with. It's matching slope fields to see which slope field matches which differential equation. Okay? So I want you to start with the first example. So there's two slope fields, 1 and 2, Roman numeral 1, Roman numeral 2. And then you have a bunch of equations. What are those equations though? They're not differential. They're not derivative. None of these guys are derivative, right? If you want to find the derivative, you got to actually find the derivative. So like, what's the derivative for A? It's going to be 0, right? Y prime equals 0. What's the derivative for, that's B? 1, right? Y prime equals 1. What's the derivative for C? 2x. So on and so forth, right? So be careful there. They didn't give us the actual derivative. So if you want to graph it, you got to use the derivative, okay? So take a second. Which of these guys matches 1? Which of these guys matches 2? I'll give you about 2 minutes, maybe 3 minutes to figure out which one matches 1, which one matches 2. The way I usually do this is I kind of see what's going on. Go with the flow. Pick a point anywhere on this graph here. Pick a point, any of these points on the graph. You can start at the top, start at the bottom, start in the middle, start over here, wherever you want. Usually I start on the left and go to the right. So usually I'll start somewhere in the middle, like here, and I'll just kind of go with the flow, see where it leads me and see what it looks like. So if I start there, I'm going downhill, right? And then I'm slowly going back uphill, and then I go downhill again, all right? What does that graph look like? Does it look like y equals 0? Does it look like,
It looks like a cosine.
it looks like a cosine or sine graph, right? It looks like a cosine or sine graph. So automatically it's either going to be F or G. F or G. Which one does it look like? It looks like sine, right? Because it starts increasing, right? Sine increases, then decreases. Cosine does the opposite. So yeah, I would think that it's F. 1 is F because it increases, because at 0 it increases, then decreases. Okay. All right. Let's start from let's go to number 2. So this guy, it looks like it's going very positive. It kind of goes like this, and then goes down, and then goes up, right? If I go down a little bit, so this one looks like it's increasing from left to right. It looks like it's, so if I start down a little further, and then it kind of looks like it's coming, then 0, and then goes back up, right? It's definitely not y equals 1. Y equals 1 is a flat line at 1. Y equals x is linear. C is a quadratic. It doesn't look like a parabola. It doesn't look like a U or an upside down U. We know it's not going to be sine or cosine because it doesn't look like the first one. So it's either D, E, or H. D, E, or H. Which one do you think it's going to be? Which one do you think it's going to be? How do you know? Pick a point. Everywhere, look at everywhere on the y-axis, the slope is 0. So that means anywhere anywhere x is 0, the whole thing is going to be 0. Well, what happens if I plug in 0 to e for x? That's undefined, right? That's not like that. So that one can't work. What happens when I plug in 0 for x over here? That's going to be 0, right? When I plug in, I can't do natural log of 0. Natural log of 0 doesn't exist. So it can't be natural log. So it can't be E and H. So the only one it could be is D. And that is what it's a cubic. This guy's a cubic. It's a cubic graph. Anything to the third power looks like that. Okay. All right, very last thing. Now, very last one. Now, 6 graphs, 6 differential equations. Okay, so the last thing we're going to do. So I'm going to give you about 10 minutes to do this one. I want you 10 minutes, do as many as you can. As many as you can. Match them. These are all the derivatives, so you don't have to find the derivatives. They're already given to you. Which one, when I plug in points, will match? That's what I'm looking for. So which one, when I plug in 0 for x or 0 for y, is going to give me a certain graph? Okay? So this one will take a little bit longer because you have more. You're going to only use each graph and each Roman numeral once. So once you use it, done. You don't use it again. Look for patterns. I'll give you a hint. Look for patterns. So let's take a look at this. So I wrote down a couple notes on here that I noticed. I noticed everywhere y equals 2, the slope was 0. B, I noticed everywhere x is equal to 0, the slope was 0. D, I noticed that everywhere x is 0, the slope was 0, and it oscillates. It also oscillates. What does oscillates mean? Like an oscillating fan? Does anyone oscillate? Up and down, keeps repeating itself. Anything that oscillates repeats itself. So like a fan oscillates, it turns this way, and then it goes back, and then it goes back. It oscillates, it keeps repeating itself. So it goes up, then down, then up, then down. That's what I noticed about D. E, it's kind of a step. And I noticed, where are those zeros at? It's when x and y are exactly the same thing. So when x and y are exactly the same thing, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, they get a slope of 0. And then D, I noticed that as x gets bigger, it gets very, very, very positive. It's growing very, very, very fast. Okay, that's just what I noticed. I just wrote down some notes there. So A, everywhere y equals 2, it's always 0. So which of these guys, when I plug in 2 for y, is always going to be 0? 3. I agree. 3. Done. B. So B and D are kind of the same. Every time x is 0, the whole thing is 0, but the only difference is it oscillates. So let's go to D. What's the only graph that we know of that changes from going up and down? Sine and cosine, right? Sine and cosine. We only have one of them. So that means this one is going to be 6, Roman numeral 6. Which is another one where every time x is 0, the slope is going to be 0. It could be 4 or it could be 2. It could be 4 or it could be 2. So I'm not going to put anything yet, because if x is 0, that would make that 0, and that would make that 0, right? So it could be either one, so I'm not ready to make an answer there. So let's go to E. Every time x and y are exactly the same, it's 0. So which one, when x and y are exactly the same, I'm going to get a slope of 0? Number 5, right? They can't, when you subtract a number that's the same, you're going to get 0. So this one is Roman numeral 5. So we're down to 3. So which of these, when I plug in x, as I plug in x, it gets extremely big? Number 1, right? That's number 1. E to the 6th is 2.712 to the 6th power. That's going to be a big number. So yeah, that looks like an exponential. So that's number 1. Okay. So let's look at the 2 that we have left. So we said B could be 1 or could be 2 or 4. That's right. Could be 2 or 4. C. We haven't touched C. We didn't touch C. Let's look at C. So C looks like, the thing I notice about C is 2 things. I notice that these look like about a slope of 1, or sorry, 1, yeah. These are like a slope of 1, right? And these are a slope of -1. So again, it looks like everywhere x and y are the same, you're going to have a slope of 1. Which one is that? 2 or 4? 2. That would be 2. If you divide the number, the same number by the same number by itself, you're going to get 1, right? So I agree. This one's 2. So that means this one was 4. Okay? So the big thing here is mainly interpreting. You're not going to have to do a lot of slope fields on tests. You might have to draw one slope field, but it's mainly asking you questions about it. Okay? So they're going to ask you 2 things. They're going to ask you, first thing, they might ask you to draw a particular solution. That's just follow the way, or just go with the flow, right? Whichever way it goes. And then they'll probably ask you to do some sort of particular solution, which what we did earlier in this lesson. Okay. All right, that's it for slope fields. Very quick and easy, quick and short.